So, good morning, everyone. My name is Claudia Gutierrez, and I'm going to introduce our work. That is, well, what you can read there, okay? Just to put you a little bit in context, we know that in the past few decades, there has been an increase on the renewable energies installed capacity of the world, and it has been due to two main factors. The first one is economic reasons due to reduce external dependency on fossil fuels in some countries, and also because of the decrease in technology prices. Also, there are environmental reasons to reduce greenhouse gas emissions and fulfill government requirements, but we have to take into account that when you want to integrate these kind of technologies in a conventional electricity system, you have to face some issues. And it has to be with the fact that the energy resources of renewable energies are variable. So this variability comes to the concept of intermittency, which means that renewable energies are not available at convenience. So also, due to that, we have to understand that electricity demand and availability of the resources are not synchronized. This is the reason why we think that understanding the spatial-temporal feature of the resources are needed for the management of the electricity system. We are going to be focused on the Iberian Peninsula with the PV technology. And it has been for many reasons. So at first place, we consider that it's a singular area with a great variety of climates in a small region. Also, we have a high potential for solar energy production. And also, regarding to the electric power, right now, Iberian Peninsula is like isolated with the rest of the continent. Well, not well connected. Regional climate models allows us not only to understand the features of solar radiation in present climate, but also we need it for future projections. Right now we are focused on present climate, but we would like to extend our work for future projection. So we have selected two RCMs by the moment, and we are going to compare them with the CMSAF data, the climate monitoring satellite application. And the period that we have selected comes from 1989 to 2008 daily radiation data. The spatial resolution is just put here, 12 kilometers. And the RCMs that we are now working on is Aladdin and Promise, that we will be adding the more models in next month. So in order to make a little bit easier the analysis, we have made a clustering analysis. And it means that each cluster that you get here have a similar temporal evolution of the variable analyzed. We first have to do a principal components analysis to reduce dimensionality, then we run the Cummings algorithm, then to get the optimal partition, we have to use a validity in this index called Kaleski-Haga. This is the optimal partition that we get, is the northwest cluster, the north, northeast, southeast, center-south, and center-west. Sometimes you know that regional climate models can present systematic bias in some variables, so in order to avoid wrong interpretation, we have decided to do a quantum mapping correction. So here you have the relative difference between the Promise and Aladdin and the satellite data. In some sense, we can see that they are like complementary because the bias in Promise is negative and Aladdin is positive. So we want to understand the interannual variability of the solar resource because we want to know if it is stable through the years. And this is the reason why we have used the coefficient of variability of the annual mean of daily radiation, and also the monthly mean of daily radiation. But also we want to know if there is some kind of relationship, it means complementarity between areas, between the cluster that we have obtained. And it means that sometimes the temporal series evolves in opposite ways, so the areas can compensate each other. On the first graph of the results, we can see the interannual variability with the coefficient of variability versus the global solar radiation. And the red lines are for the mean at the Iberian Peninsula. Green dots are PROMES. The satellite data are in blue, and the Aladdin data are in purple. So in these four graphs, you can see that PROMES is over the satellite data for the coefficient of variability, and Aladdin is underestimating the coefficient of variability. If we focus now on this area, that is the north of the Iberian Peninsula, the models here are just representing well coefficient of variability, and it corresponds to the area that is on the north of the Iberian Peninsula and it has a higher coefficient of variability. In these two graphs here, on the other hand, we can see that the area with a smaller coefficient of variability corresponds to the area with the highest resource. Here we have represented the interannual variability of the monthly mean of daily radiation, also with the coefficient of variability. At the eastern side of the Iberian Peninsula, the differences between winter and summer months is smaller. While if we focus now on the western side, we can see that winter month is higher, has a higher value, reaching almost 20% in winter and 5% in summer months. The orange line is for the satellite data. The dark blue is PROMES and the light blue is Aladdin. So you can see that in most places, the Aladdin is under the satellite data and PROMES is over the satellite data. But there is an exception in the North cluster that for most of the months, the satellite is over the two models. Well, we wanted to understand complementarity between clusters, so we have calculated the monthly correlation coefficient. So also we have represented here the annual cycle for each pair of clusters. But there are some cases, well, the red line means the no correlation, but there are some cases that are not relevant for our study, but because as you can see, the correlation coefficient is positive and high during the whole year, but there are other cases that we want you to focus on, and we are going to go into detail. Here we have the northwest-southeast cluster, and we have 2 points where the correlation coefficient is negative. So it's here in February and also in July. So these situations are important because it means that the two clusters are evolving in some sense opposite. If we focus now in northwest center south, we can see that there isn't a situation with negative correlation, but there is something interesting, that is that for the first step from February, for the first half of the year, the correlation coefficient starts being positive and high, but it falls here at the middle of the year to start to rise again then. If we look here to the north-southeast pair, we can see that also we have here in September a negative correlation coefficient. And if we go now to the north-center-south pair, we can see that the evolution is similar to this one that we have here, starting with positive step from February, and then it falls down again to rise. So just a little bit talking about energy production, because in the end it's our objective. We know that variability of the solar resource comes to a variability of the photovoltaic energy production. These preliminary results only show the annual mean of productivity, which means kilowatt-hour per kilowatt installed. For that, we need to first calculate the global effective irradiation, and also we have considered the tracking system of the PV modules. You can see here the annual productivity by clusters, and the orange bars are the two-axis tracking system. The dark green is the one-axis tracking system, and the fixed panels are here represented with the light green. It's important to notice that, of course, for the two-axis tracker system, the productivity is higher at each area. But I want you to focus on the differences between the two-axis tracking system and the fixed panels, because it's important to notice that at the places where there is a higher resource, like in center-south or southeast, differences between the fixed panels and the two-axis tracking system is higher than for these areas in the north, for example. The productivity can increase more than 45% for this area. And to conclude, variability of solar irradiation is higher in western Java North regions of the Iberian Peninsula and in winter season. Relationship between clusters, so certain grade of complementarity in some areas. Differences between the two RCMs illustrate the interest of using a multimodal ensemble, and the differences on PV productivity for each tracking system, so the importance of taking this into account. And this is the further work. Of course, add more regional climate models to analysis, a deeper study of clusters complementarity, and analyze the future projections to understand solar resource variability trends. Thank you.